Network Spotlight series. I don't know how you feel, but for me, I think the last Spotlight was in late November, so it's more than a month, which at ITU time, it's like quite a long time. So I'm very, very happy that we're all back and that we're able to host a presentation and a scientific talk at a very excellent level, but also with a very important and interesting topic. So when we think about AI, and maybe even when we look back into the last year, I think we're pretty clear that by end of 2025, most people that are interested at least to some degree in technology, they now understand the term of AI, they know how to use language models, at least in text editing and conversation. Some even start building agentic AI. But nevertheless, still when we think of AI, when we maybe even go out and ask people, mostly we think about software, data, algorithms. So what, however, is important to actually leverage the full potential of AI, especially in industrial applications, but also in a wide variety of societal applications, is bringing AI into the physical world, bringing AI into reality. And different terms have coined in the last year, but some terms that are very important, and they also will be central to our talk today, are physical AI and edge AI. And so I'm very, very happy that at ITU, where we're dealing with the frontier technologies, AI always in combination with some relevant domains, that we have among our professors an expert in specifically that level, physical AI, edge AI. And I can already promise you that it will be a very kind of engaging talk. And I'm really looking forward not only to the talk, but also to our conversation, to our discussion afterwards. And with that, I would like to welcome our Professor Michele Magno and wish for a warm applause. And then, Michele, the stage is yours.
So thank you very much. It's working? Okay, thank you very much for having me here. And for me, it's a great pleasure. And thank you very much for a very, very nice introduction. I hope you didn't bring expectations too high, but I think it's, as I mentioned, my pleasure to give you this introduction of sensor to intelligence and what I believe is happening in the AI, where we are bringing AI more and more on the physical level, and we see what this means. So probably you already see from, working? No. I don't see also here. I can do by hand here. It's not moving. I think it's frozen. Maybe wait too much. Try with and okay. Okay, good. So very briefly, you probably saw. So I'm also head of the Center for Project-Based Learning in ETH Zurich, and I'm leading a research group on embedded system, in particular smart sensing systems. I think there is a bit of curriculum, but what is important for me, and also what is the connection with EU, that I'm a fellow professor here, and I'm leading both emerging sensing systems laboratory, and also the project-based learning center with a CubeSat project we are going to show in a few minutes. The reason why I'm introducing it, because I think the reason why itu had interest for me was actually because in a few years ago, so in 2020, in the full COVID time, I started in ETH this project-based learning center, and I would like to share a bit of some important key learning aspects that I learned from here. And there I was alone, so in 2020. And after 6 years, so now in 2026, this is a reality that is actually partially self-founded directly from my research topic, and we are employing 30 people. So a lot of work you are going to see in the research and the teaching in these slides are actually coming from many people working in the project-based learning. And as you know from also itu, that is one of your teaching skills or activity, more and more we talk about promoting this developing creative critical thinking, problem solving abilities, and communication skills. And if you see different papers, there are many ways that you can integrate theory and practice. There is a motivation that we want to give the students, and they are able in teams or alone to have this project management and the soft skills that are improving. And there's many, let's say, interesting topics and action that we are doing with students for teaching them how to tackle real problems. And if you see in practice, and this also, if you see in 2025, also ETH say that this is in their plan for developing teaching is some things that they would like to promote. In practice, if you see better many of these topics, you have many ways to integrate them. And this is because I start from here, because I would like to show what with my staff, but in general, what I promoted in ETH in these 6 years and the connection with the research topic that actually Daniel showed before. So in practice, I think how we implemented it, I think we strongly believe that to give opportunity to learn to the student, you need to allow him to bring a strong theoretical foundation and practical application. Means that also the theoretic part is quite important. And this I call what I call the stage number 1. So what this means? And then it means really giving, and actually this circle was awarded from this ETH Kite Award, is a teaching award that ETH is giving every 2 years to different projects. So it means that in stage number 1, we are helping students to develop even further some things important from a theoretical level. And in particular, you can see also from the number, so in ETH, we were proposing this new 50 project seminar classes where we are dividing the theoretical content with practical skills. What this means, for example, there's an example down, we are teaching them to do machine learning before to put them in the wild to do machine learning in a project. So I think this is some things we see that is actually something quite important. Students are not coming often with a background that can exploit to do practical job. So it's not, from our experience, very good to put them in a while so you will learn. No, you need before to give theoretical strong foundation, then you can make them doing project. And then you can actually develop it in their master student, in project, other project, hackathon, contest, small project, where the student can develop these skills, and then only there they are ready to go in some more interdisciplinary project, and these projects are going then to be more or less successful, but for sure they are allowing the student with all the levels, especially for the people that have a different background, to build the missing skills and the theoretical background to really go in that stage to be ready to face problems. So we need to allow students to develop something strong to then go in something practical. And this is also why I wrote down is not an exclusive club, because in ETH, this is an example ETH that it's, you know, I come with this architecture to actually avoid that in ETH we get only the 6 best students and we make them do a project, and then we say, well, look how good are the students. Yeah, the best 6 students are good, but what is the other 1,000 students that are not having it? So when we say not exclusive club, I feel this architecture allow all the students with all the different backgrounds to grow in this system. And of course, a student that has this theoretical background can jump here or here directly. So this is the reason why it's a flexible structure. And then you will see also what is this 4th level there. And then in teaching activity, we were also successful to get different funding, and for teaching funding, this in 6 years we raised under 50K, but this is a number, remember, for later. And then you will see also what this means for. But what allow us to give to students and what we get back from students in this what we call flagship project. Then we are having skilled students that can make some things quite complex. We have many projects that we call flagship project, means that there are interdisciplinary projects where the complexity of the project requires to have a team of students working on it, not a single student can do it. For example, we have students that were designing an open platform. You can see the similarity for the Ray-Ban, so there's some open platform for wearable. We have students after their work are now running 4 different startups around Zurich. Their students are also having some interview with the press, and there was a very good atmosphere. And actually now we have this Forza ETH team that was started in our center. That is an autonomous racing team that autonomous is raising money and is continuing to work in autonomous racing like a student circle. So there is many things that were going, and also this is an example why I'm bringing here, because this is some things that I'm building, especially with Luigi that is already here, like postdoc. We would like to do something challenging, also having in program to give some technical skills to the students to get some content, some modern scientific skills, so some things that really can be useful also when you're going out of it. So the project is quite challenging. We would like really to have a CubeSat, and also with the help of Wolfgang, we would like really to launch it, and we would like then to show that students with this project are able to launch it, to make some things, to make some things that it's successful and challenging. And why I'm saying now I'm jumping a bit of research, because I don't want to not cover the topic of I mentioned in my title. So I think why I'm saying the importance in research in PBL, because actually I strongly believe that teaching and research need to go together. So I think to exploit the time, or exploit is not the right word, but in general to maximize the time and the effort that a person that is the teacher, it's putting on the teaching to give to have a more skilled person doing the research project. And I think this is the reason why there is effort there, because in reality I really feel this is a circle. If you do a very strong, you build a strong theoretical foundation to the student, you cultivate their activity in practice, you make them doing challenging project, not easy project, but also easier possible, but in general challenging project, you can bring back. So I have an example of many students that were doing a flagship project and now are PhD part of my team. And why I'm putting a circle, because if you push up the excellence in your research, is the only way that you can push up the level of your flagship project. I think at one point you finish the idea if you don't push back research and together. And you need new people skilled that are helping you to do research to propose a new project. I think in the long term, I feel this circus can be sustainable for the reason that you get skilled students that are back your PhD and back in research topic. And also because I feel financially, I know what is the situation here in Austria, because I'm more confident with the things happening in Switzerland. But you remember, I'm the same person doing the same topic. I took 150K, very, very successful. But what I did in research, it's 40 million. So 100 times more, this number is even higher now. This was a few, but in general, this is 100 times more in research funding. Why? Because you need to be actually different from the other groups that are around the university to make some things that attractive in terms of European funding, national funding, and industry cooperation that are going back this circle. So this actually, it's also my motivation. Why I should put a lot of time here to get the best student skilled, to get back the best student research back there. And this is a circle that is sustainable. So today, actually, my center, that is a teaching center, but this is not recorded. I will not say to a teacher, I can work without their money, but they just relying on my research money, doing both research and teaching. This is because I feel the connection, it's strong, and also it's actually a pleasure. Of course, this requires a few years to get this circle working, but it's something that is working very well. And of course, when you do research, you need to start to narrow down, because there is no group that I know that can do research in many, many topics. And this is the reason why my teaching center that started with a teaching center 6 years ago, today is actually a research center that pushes the teaching higher, and is in the topic of the edge AI. And my talk now, my research talk is more talking about what is the edge AI, why we are more interested in physical AI, and how this edge AI topic in terms of research can cover different applications. So first of all, I think some things are important just to see this division, especially for the people that often are used with only AI. And probably you know very well, there is a lot of progress of AI, are very good progress. And many people are still believing that the majority, still is actually the reality, the majority of AI today is in the data center. So the data are flowing from Internet of Things, or for sensor, through the wireless 6G, 7G in the future, from the network, the IoT gateway, or in general from the internet gateway, and then it's going there to be processed. We are very happy with this approach. For many applications, yes, we are very happy. Today, my father is 18 years old, was calling me in a range of probably 10 times per day to tell me the word is not working, how I can correct these things, where I found this information. My father today is able, I told him, look, install ChatGPT, use it, look, ask him what you ask me, and he will reply very well. So, and actually it's working. So today, now he's calling me, actually I'm calling him every day to see if everything is okay, because it can be that he's never calling me because all his problems are solved. So this is because the AI cloud, he has only computer problems. So this is very good to solve a computer problem, and people are asking, it's working perfectly. But what happens if we start to move the AI in a real world where the things are happening here? For computer people writing, this is still the best solution. Yes, this is still the best solution. Because you have a computer attached to the PC, it's still working. But what happens often, the real world doesn't happen in the cloud. The real world happens in the physical world, as we mentioned. And here there are opportunity and challenges. So first opportunity is that we are moving the AI in billions or millions, I don't know how many there are, of devices that are different, that are integrated sensors. So it means opportunity also for cooperation, industry cooperation. It means that there is an industry that is doing wind turbine monitoring, industry building autonomous drones, phones, autonomous cars, etc., etc. And we are sharing the same technology. And why this is even could be interesting. So there is the problem of, and this is actually our challenge of the battery. The majority, not all, of these systems are battery operated, or they are relying on small hardware, but can be that they don't have hard verified access. They often need to work with lower latency. You need, for example, to stop your car autonomous without relying on Wi-Fi, and you need to be sure that your car is stopping in time before to kill some person, for example. So it means here there are other constraints. It means that actually, you will see later what this means, but take now the things that are right there, that actually exploiting or integrating AGI with sensor fusion, we can have efficient systems. And then I will say how this can happen. But before, I'm going to stop 1 second, I think it's a brief a bit, to see, for example, this I put recently, this slide, because I know that you know that your colleague here in JKU, they always claim they invented the LSTM. You believe how this we are doing very well, but let's, there is audio? Otherwise, I can say what this guy did. This guy is the one that was invented transformers. And if you hear this interview, I think I can tell you what he's saying. He's saying something very crucial that's still valid today, and still is the topic, central topic of AGI, physical AI. This guy said that LSTM were very good, but maybe too much complex to the problem they were solving. So, and for the computer processor that are not changing so much from last year, we are still silicon processor, we are not ever ready for quantum. Basically, if you are training LSTM memory, very complex network, with the amount of data you are having, you were using a huge amount of time that was better training a small, not complex, full connected layer to do the job better, because we were better training. This was the motivation of inventing transformer. And they didn't invent the transformer. Actually, they exploited efficient mechanism, the attention mechanism, done by other people, not the people who did the transformer, did the mechanism, that they were efficient in the hardware. So it means that they had hardware a problem, they have a single problem. We want to do a new model because we want to have intelligence that are trained, in this case was even trained faster, to have a better model in terms of training time and speed, because the computers are not changing. So the computer architecture, I know that many people from software, they believe that they can put whatever memory because anyway, some hardware people do better. No, in hardware and software, there is no magic, impossible to do magic. Also, black box approach is some things that should be always avoided. If there is a black box, for sure you are going in trouble, for sure, because you don't know what is happening. And especially in hardware, it's some things that you cannot really control. I will show you later. But this also is interesting that now DeepSeek is doing the same approach. Basically, in the time, LLM become bigger and bigger and bigger that are saturating what an hardware can do. And an hardware person, I'm actually a hardware software person, but by nature I'm a hardware person. I'm telling you that we cannot do miracles, impossible to do miracles. And the only way to do is that you can do the things more efficient to go fast. So why we need to go faster? So why we need to go there? Why this DeepSeek was so successful? Because actually they did the same job in terms of accuracy using less memory and less operation. Did they do magic? No. They can exploit or open the box to understand where are the inefficiencies of the software to make some things that have the same performance using the same hardware. So why this is important? Why this is connected to the physical AI? Because this guy here is the CEO of NVIDIA. And the CEO of NVIDIA, this is because today we call physical AI, I was always calling it a cyber-physical system, but it doesn't matter. Say that many, many years ago, perception AI, 2013, so 13 years ago, was the hot topic, solved. Then arrived generative AI with transformer, LLM model to understand the language, to understand my father what he's asking, I give a response. Solved. 2017, 8 years, now it's 9 years ago. Agentic AI, solved. These agentic are working because it's not magic, are consequences of this effort. Of course, it's not really solved, it's mature to go in the market. Now, what are the challenges are in what means physical AI? Because we are going in something more complex. It's not that it's old or not continue to progress. It's just that we are exploiting something that today is consolidated to do something better, Here it's where we are. And why this is so complex? First of all, I need to go back on hardware. Sorry for the people who are not in the hardware domain, but I'm explaining why I'm saying there is no magic in electronics. So this seems very complex. In reality, this is saying something very simple. I'm saying that why NVIDIA is the best, so this means that this is the power versus the operation, how much faster your processor can run. Why NVIDIA can do it very well here? Because in the range of the same power is the one exploiting the higher peak for power. It's the better today, you have the technology to give the higher peak of power. But if you have the problem to don't run, this means that you need let's say, a nuclear plant to run many of them. This power is more or less, if you multiply 400, is what you get from a city power consumption. This is because they are doing data center. If you move here, where you are in domain to work with the processor that can run with your battery in your phone you have in your pocket, means that you have significant, even if you call NVIDIA, here there is no NVIDIA architecture, but let's assume they are NVIDIA, you cannot do better than this. You cannot do, because the number of transistors to get this little power is way smaller than the number of transistors here. Less memory, less processing unit. Can you do better? No. Because the silicon, the Moore law, is telling us that every 2 years of 18 months, you get double power. So 1 year and a half, 1 year and a half, 1 year and a half, 1 year and a half. To get the performance that today, this is even more, but in general, to get the performance that today we are having on 10 watts power, you need to wait 7 years. So to get the performance of what is here, you need to wait 50 years. When your algorithm today you want to run from here to here, I will be obsolete. You see what happened from LSTM to transformer to other models that are coming today, 2-3 years, then there is something bad. So this means that to go here to run the physical AI in the existing platform, no one can do better than this platform today. What you need to do, you need to either exploit the processor arriving, of course selecting the edges efficient processor, or if you want to get this target, you need to do some things different. First of all, an hardware person is telling you don't rely on hardware. Because we cannot do, nobody, even if you call NVIDIA, if you call Intel, you cannot do double performance every 18 months. But Fortunately, you can work at a system level and application level to make this target possible. And this actually is the interesting, become a bit more complex, but interesting part of bringing AI at the edge or in the physical world. That you can play with much more tuning section. It's not only the software, the hardware you cannot change, because also you cannot change your NVIDIA Jetson every time, but you can play on the sensor data. For example, this is an interesting example. So this is a novel, relative novel. Now it's already 5 to 10 years that is out, this camera. This is an event-based camera. It's a camera that for each pixel, instead to give you information of 2 or 4 bytes of the color of your pixel or your t-shirt or your jumper, is giving you only the information if the luminosity of this pixel change in positive, white, or in negative blue. If you see black, means this pixel didn't change luminosity. What this means? Means that you can reduce the data to understand if an arm is passing in front of the objective of 1,100 to 10,000 times. Means that, remember this efficiency, you already go to use 10 times, 100 to 1,000 times less memory and less operation. So with the sensor, you don't need to change your model. You need to change actually your sensor to speed up. In theory, then it's not really this. But the sensor play an important role. And of course also play an important role, as I mentioned before, moving already what is called today AGI, eventually sensor fusion, to increase the efficiency of your algorithm. You know that you are running in a limited hardware, you need to rethink, redesign your model. For example, what I mentioned, transform, maybe changing model, because this model for your application is too complex for your hardware. So this also can speed up another 100 to 1,000 times. You don't need to wait 20 years to get your model running. Actually, you can modify your system, your sensor, and AGI. Means that black box approach, forget to use it. You need to understand what AI is doing, changing it according to your sensor and your hardware. This is because it's important to go deep inside. The same approach, but I'm not talking in this talk, is that you can do the same for the efficiency of the communication, setting the energy in terms of battery, for example, higher. And also what is interesting in physical AI, so these 3 topics are more or less technology topics. You can see, but you can see very well, I put some application. So there is an autonomous cars, that is used for object detection, there is wireless communication. So it means that in physical AI is actually crucial, as you need to eliminate the vast of the model and the data and open the box to do only what is necessary for what? For your application. So application in physical AI is crucial. You cannot take a black box approach of people that train your model to do Coco data set or whatever, to do surveillance, and then you want to use it to do the object detection. Will not work. You need to use the minimal to do it, and I will show you why this is effective not only for the energy, but also for the latency. So this approach is some things that actually we are trying, also would like to try to develop here in itu. So this approach on efficient to all the aspects of the systems, from the hardware, from the software, for AGI, for the sensing, and from the application, in my opinion, is crucial to be successful for the next generation. And I would like to show it, because this is actually this research topic were the way that we brought back to the students. And here you can see 2 student competition. Why efficiency is important? Actually, I'm saying this before you are asking some question, because many people say efficiency is only for the battery-operated device, a drone is or robot is consuming so much, who cares of energy? No, it's wrong. If you do efficient operation, means that you reduce the memory you need with the sensor, the AI part you need. In reality, you can put in the same hardware, a car is an hardware pieces, in the same hardware you can put much more intelligence and doing your complex stuff faster. What is the results? That you have a car In this case, we implemented the reinforced learning inside the car, not outside. In the train, the car was learning faster to beat the best of our algorithms. How? Efficient algorithms and more complex stuff in the same hardware. So very fast in one side means time is learning to do faster than the others. So you save a job. You need to save energy or no, we don't care to save energy. But if you have the same hardware and the same skills, you go faster to anybody else. If you do an innovative project, go in Ferrari, tell you, okay, my system make you win all the competition. The other system I took from Google, and here they say, okay, I can take also from Google. Why I need you? So you need to be successful, be there, and if you teacher, we teach the student to be creative thinking in understanding. You can do it without having a technology background, impossible. And this is another example. This is even more complex. So we start from scratch. It's an autonomous robot that you are having. What we did here? We did the demo. We make the student make a play with the demo. No, we were losing this competition. I want to go there. No, here we spend quite a lot to send them. We want to go at least to be the best three. To the one. What we did? Okay, we need to open the box. Let's remove all the software they did, all the embedded control they did, all the hardware we did. We need to put only the things we are doing, how we can do it. You see this actually, this orange box here, it's a custom hardware software systems. We really start, we need 2 years to arrive to this level. That has all the reinforced learning control. We change the camera, we put the camera where we want. If we want to add another sensor, we can do it. According to the application, we can change it. And this robot today, this actually is our training room where we train in the unknown. So we train him not to recognize the path. We train the robot to recognize how react autonomously to some things that he doesn't know. And because this is what, so we train it in many ways. So we were there in this international competition for the first time. So my target was be at least the best three. And actually, we were there for the first time. We were the only people that changed the hardware software. The only people. What was the results? We were very scared. The results were we won 2 competitions in one. We were the only robot going up and down the labyrinth unknown for 10 times robustness. And we were the only lab that was able to do it faster. Robustness, more complex, latency. Energy we care? Not at all. Actually, we are putting extra hardware that is giving more energy. So this energy is, from a power perspective, worst. Intelligent, why better? Flexibility, we can change it. We can put whatever sensor we want with. So again, it was 2 years work of 4 people, but today we have the capability to do it. And same, this is also what happened from implementing the system without reinforced learning on the car efficiency to implementing it from the 3rd place in international competition, 1st place in international competition. Same people, same hardware. So these, I think, is some things that I hope motivate to do research and teaching together, and also to show that these topics are quite interesting, and also some things that attract quite significantly the company, because the company see that these actually students, this project, I'm not doing it, students are doing it, they are able to make the jump to some things that they might not do. And this is also what, this is an educational kit that we are using, but the idea that we are having also with Luigi Capogrosso, that is postdoc working on it, is that not only by it and putting in the space, but also we are trying to change the hardware and the software to have a flexible system that we can reuse, not only to do some things more than what we bought off the shelf, that is good to start to work with it, but to do some things more. And actually, it's interesting because this project that we started only a few months ago is already bringing some accepted conference paper, still a conference paper, to do Earth observation using what? Exploiting an hour source of information like the event-based camera to check if this event-based camera can support the efficient machine learning that we are implementing in this hardware that is partially novel and supported by the lab, in this case, that is here in itu. And just I want I think I have still a bit of, I think still a bit of time. I want just go back to the robots because I really feel, so I think, if you see all my publication 4 to 5 years ago were pretty much in an intelligent sensor system. And why I think we were so fast to move in the robot, because I really feel that actually a robot, this is because I like a lot, a robot, this physical AI, this magic physical AI world, in reality is an hardware software architecture. So it's actually a pure embedded system that get sensor data from the camera, from the NASA sensor on the drone, and is doing a signal processing embedded to react to the physical world. And actually, these are some things that can be used in many, many different application scenarios. You can have a monitor drone. You can have also the sensor system that doesn't need the robot to make the structural report. We can have drones that are going through different industry application and environment to get detect and make monitoring. And you will see really at the end that also manipulation is something. Actually, something is happening. So these actually is a sample of soft robots, are a sample or drones that are flying. A few of them are coming from ATH, few are coming from others. And actually, I have a little demo that we are seeing also our approach in opening the box. For example, also you will see that I will try the end to this. But in general, I think it's quite a strong demo to show that we modify, this is a platform, this is a Crazy Fly platform you can buy. We modify also in this case hardware, software to push inside this platform more sensor, more intelligent, pushing on efficiency. If you buy it, usually you can control with your remote phone. You will see that I don't use nothing. This drone never saw this room, so I was up before, and never make him training in this room. You will see this flying in autonomous. This I'm trying also with my daughters. They are my, let's say, test people. It's very safe, and they are able to control it. So this is actually the demo that I'm using for my daughter. It's even not our best demo. So why I'm thinking this is quite interesting, because to scaling up this robotic view is actually you need to do more or less what are the topic that I was even envisioned before the robotics. So we need to go in and make a signal processing, whatever this means, including AI. But for me, it's a signal processing to use sensor data that are processed at the edge, means in an embedded system. We need to have it for having low latency and no data protection as well, but also not dependency from the Wi-Fi and the cloud. We need to have eventually infrastructure-free system. We need to work with the technology. We need to work with sensor fusion to make it more robust, more efficient, to have more complex. This is actually more and more we go in robotics, more and more we are going in a complex system. So one thing is making an autonomous car running in highway. One thing is making a robotic here, understanding if some person is sick, and then make an action and not falling on him and take the right action. So the complexity of the intelligence is increasing, and the hardware is not scaling so much with this complexity. So this is important. Efficient algorithm is important, efficient system important, and also there's many topics we are trying to do with collaborative. And in general, here also I want to show the importance of having the different sensors. So often the camera is quite good, but there are many different sensors that can reduce the complexity to accomplish a task. In this case, there are many things we are working from the time of flight sensor, radar, ultrasound, but I want to show an example because this is some things that we were believing was even not possible. This is the same drone flying. Often, if you go in a known area, you need a SLAM algorithm to understand and mapping your environment system. The robot usually today, you see, I don't remember if it was in the lab up or here, but I saw this robotic, the one that are the cleaner. There you see there is even ladder there because you need to go in something similar. This ladder usually costs from $700 to $1,000, plus you need a big processor that costs, make power, is sucking the power. And then we say, what happens if we are using, this also we were lucky to work with ST Microelectronics, that they give this sensor 2 years before the market. These are little time of flight sensors that today are commercially viable, that are giving you a picture of 8 by 8, giving you the distance. So is this possible to do a map, maybe distributed map, without having this expensive LiDAR? So actually the same system you see here. Very light. This is weighing few milligrams. You can see that the data are bad, actually. So when you use some low power sensor, often you have some data that seems very bad. But if you embedded your algorithm for correctness error directing in one drones, I think this can be significantly correct. And this is interesting because this power consumption, in this case we were using a novel RISC-V multi-core processor that is designed in ETH Zurich from another group, but we were able to use only 88 milliwatts to make a pure SLAM distributed system with LiDAR-free, with an accuracy. Of course, I'm not saying here and never will say that this accuracy is the same LiDAR. LiDAR is giving accuracy 0.5 centimeter probably. But still some things that for main application, for example, the cleaning, for example, not crash the drone when they're going in some pipe, is more than enough. And then you can see this actually was interesting, but this we send them back to the student. I think I put the other video, but there is also a video where students are building actually this ecosystem. Students are able to make a data set. Students are able to enjoy the work of the digital drone, but you can see there is a lot of push the research that is going back to them. You can see that the data crap at one point, the system, there is also ultra wideband to coordinate the different drones, but at one point, the student arrived. At one point, the drones are able to find not only the street, but also give a map of all the system with a pure LiDAR free system. So I think this is, I can go a bit faster here. And also, we work also with higher drone. If you open the box, you can really go from a small drone to bigger drone. For example, in this case, we were using a camera system. We were exploiting the event-based camera inside the drone. This is also actually an open platform we are releasing, designing in FPGA. There's an hardware that we are doing for detect this drone. And this also is interesting, this camera. I think I can make you imagine what you can do this camera. So just to give an example, here we are going very slow. In reality, this camera is able, so we tested it in Zurich. It's possible, everyone has, it's possible to shot in a shooting area. We are able to see a bullet passing. So it means that these are effective ultra-low latency system, and if you do your algorithm to get this bullet passing or to get a very fast object passing, means that you can drive your drone in a much secure, or you can be more reactive to the system. And this is back what we designed to have some more details. So in general, all the hardware platform in the same way. You can see here, for example, we are using also LiDAR, but in many competition we remove it. There is different sensor, but in this case we can use, so this is because we are not against any sensor, but in general, with this configuration, you can use the sensor system and the sensor subsystem or the sensor technology or topology that you want, changing it. And maybe for some other application, it's better to put the sensor down. For other application, you can use a different topology of the sensors. For example, in this case, we were using then the RoboDog to find the crack. This actually is an European project that it's running for next 4 years, where we are using robotic dogs to identify the different cracks in bridges and in different buildings. And this also, of course, is a combination of AI that you need to run on the robotics part with different part. And also this, I think, then I'm almost to the end of my presentation. I'm going for the demo. So I think also some things that is today more and more, I think there is a lot of humanoid system. The technology doesn't change. So actually, just making even more complex. So the complexity is growing. But in this case, for example, we start to see what manipulation can do, because you can have an action and reaction of the RoboDog. Of course, these are some things that we started only 1 year ago. There is not much, but it's interesting also for the control system. And from wearable, we have many devices. In this case, for example, we were investigating on merging the vision from the RoboDog with the vision of a person to have a more user-friendly human-machine interface. In this case, we merge, so all these algorithms are running on a microcontroller. What we want to merge is the point that the person is looking and matching it with the robot view to get, for example, an object, or to help some people with some disability to open a door to make some action. So these are things that still we are working on it, and also you can see that we have many tests in ATH. This is particularly interesting because it's the combination of the coordination of this robot dog with the autonomous system. So the idea is that we want to see how we can coordinate that. These are actually magnetic antenna to be very precise in moving and to make follow the drone 100% with the robot dog, and then the little drone can accomplish other tasks. And with this, before to conclude, actually, I promise a little demo. So I think this drone is one of the many drones we are having that we redesigned the hardware. And actually, I need to call the student to say the trick, because for security reasons, he put an activation before it was in timing. So in reality, when I'm putting the hand on it, he will recognize my hand, and it will start to fly to an altitude of more or less 90 centimeters, at least what they told me. So I should, at one point, okay, it started. So it's designed for safety reasons. You see that sometimes it's running. So it's designed to be in a static position or with little movement until I'm not going closer. In this way, this is actually the demo that I'm bringing to the school of my daughters. In this way, they can control the drone, and you can see never saw anything here. He recognizes, he's mapping a bit, he finds a stable position. You see there, I think probably saw something's black. So he went there to Stephanie, then stop. don't hurt her. But anyway, now it's programmed to fly until someone is deciding. Actually, should be some few. I think, the command I remember more is that I can push down, and if I push very down, it's stopping, it's landing in safety. But there is also some way to bring it back. You can see that there is also some way to crash him, but I don't want. So I think if I give it so much noise, you can see that it starts to be unstable. But if I want making landing, okay, now he landed in not a stable position, but in general, it's some things that can go. And this is, I would say, how we did it. We need really to redesign all the control and the intelligence on top of it. And actually, in this case, we are using a standard processor that is inside this microprocessor. We don't extend. There is only the sensor, if you want to see later, that is on top of it. But for example, we have many other versions that are integrating more sensors. So in conclusion, I think you are tired of hearing me. So I strongly believe that actually novel sensors and sensor fusion is a key game changer. So I think today more and more we have sensors companies, but also research groups that are providing excellent sensors, and we should not stay only on computer vision. Computer vision is actually a wonderful topic. I'm not saying not only computer vision, because many things can be done changing the sensor, not only in robotics, also in other parts. And having your hand on low latency decision making is not only energy for battery operated devices. It's also some things that extend your capability a parity of AI or complexity of hardware. So it means that if you are going to open the box and understand hardware software, you can actually do something much more intelligent than you can do without opening the box. And finally, I think it's very important application. You see there we're ranging for different applications. If you see my publication, you see that we are going from implantable robotics to project with Ferrari and autonomous cars or profiling of street. And we are the same person. But I think the technology behind is that if you do and you push efficiency in hardware and software co-design, especially new sensor, I think there are several applications that can be solved today. And the final, I really liked, and I still feel this is a winning solution, pushing and combining research teaching. Because this maximizes back to efficiency the time of a professor, a teacher, or researcher to do it. And this, I think, and also it's something that, in my opinion, is nice to see the growth of the student. And if you get them motivated in these some things that you can see, actually, I would like to be student now because you can try many more things that I was trying. It's some things that is quite interesting. And then in this group, I need to thank because many of the things you see from CubeSat actually are coming from the few mounts that Luigi is here, and many of this work, of course, is coming also from a group and from many cooperation that we are having in a European project or with industry cooperation. And I'm closing here in more or less time. I promise 50 minutes. So it's, and I'm open for any question you might have. Thank you very much.
lot, Michele, for this inspiring talk, and also it opened like the portfolio of not only the research that is going on at ITU, but also the special educational model, the project-based learning you talked about. So I would like to open the floor for questions on the research side, on the project-based learning side, on all the fantastic things you saw today. Procedure will be that we have a small micro, and I'd like it to hand it to the first question. Who wants to start? Chris.
Thank you, Michele. Very impressive range of projects that you got yourself involved in, and range of work, of course. Your idea of efficiency kind of comes mainly from kind of being very clever on the sensor side and really being clever about the kind of data that you use, and then use that in small, edgy kind of ways, right? And I wonder what your thoughts on changing the system, the AI models themselves are, in a sense that, you know, we had this change of STSM to kind of transformer models, but then also, you know, there's now a big question about using subsymbolic and symbolic AI in some clever way together. You know, being clever on that side, might that also be like a lever that would help you to make similar efficiency gains on the edge, right? Not just like about the data and battery and power, but also on the models and idea of AI itself, to kind of get smaller AI?
So in general, I'm, let's say, I feel, remember, I'm an hardware person. I feel our limits are always the limits that the processor platform is giving to us. Because today, whatever we think in terms of algorithms need to run, especially in edge, in a real hardware. So to reply to your question means that yes, for sure. Because actually, we need to think more and more what is efficient in terms of how many operations this new model are able to give me in the current hardware platform. Actually, things are going together, because then usually what are doing the hardware designer? Are doing what the hardware is doing better, and where are the limits of the software? And they're trying, actually, they're coming together. What happens often is that either the hardware designer are doing what is easier for them, or the software designer, this is even more exponential, because hardware has more constraint, are forgetting that there is hardware limits completely. So this is actually the sample transformer. The transformer came for a single reason. They were unable to run in existing hardware. So one or two persons that understood these limits say, okay, let's see which mechanism run better. Not in terms of complexity, because LSTM is able to do much more complex tasks than transformer. But badly if you don't have enough time to train it. And then they cleverly thinking at hardware level. Same things today, what is doing NVIDIA? What is doing NVIDIA today? You see the limits of having this float implementation and the opportunity to give a 4 bits opportunity in quantization. And this is going together. The people that understand in software that the 4 bits quantization is arriving are matching things together to be faster than all the others. One of the things that DeepSeek did is actually the changing. They didn't change the model almost, so a bit yes, but they didn't change significantly the model versus ChatGPT. But they changed the way to train it, a smaller model with transfer learning, to train better the model, extreme quantization, and pruning. So why I'm saying black box approach, I don't like it all. Because if you use black box approach, you cannot do pruning. You cannot understand where are in your model the inefficient path. Always there is an efficient path. No one do a model that works because you have different operations. So it's impossible that in a model there is not inefficiency. And this is a field, so to reply your question, of course, yes. And actually what we are doing is not only in sensors, is actually open the box. So this is because I feel in AI is even more important. I feel the speciality of my group come actually for the fact that we are hardware software person. So we are able to do, and I'm saying I'm not doing magic. If you ask me, everyone call me in a conference, but how you do Pianissimo YOLO for 6? No magic. You see inside whatever our limit. Our limit was impossible to do these big size of images from 64 to 320, we need to go to 88. But you lose accuracy. Yes, there is no magic. If I don't cut the input side, no way to do it. Then 8 bits, training, further training to the knowledge and distillation happen. You check it, you do the calculation, works. So, and when you see magic things box, for sure there is a hidden path inside. So this, to reply your questions, yes, because fortunately, the limits are everywhere. So it means that people in algorithm are studying no way to exploit the hardware, the people in hardware are doing no hardware, but it's going slowly. It's not going fast as we believe or we hope it's arriving. So you need to creative, including the sensing and the system level optimization. Thank you.
Thank you very much. Also, you mentioned you reduce the amount of data that needs to be processed and use more efficient sensors. All examples you showed were basically with visual signals. Do you work with other signals that we encounter, mostly audio signals? In the real life, we use a lot of audio?
So in general, this approach can be used on all the kind of sensor, because the way that they are doing it, also the people doing event-based camera are not doing magic. They are doing an hardware processing that make the difference between the 2 frames or 2 pixels, and they are giving input. So they are doing pre-processing before to give your the data. And this actually can apply to also audio data. So what is the drawback? Because this I didn't mention because I want to show you the best part. So I can demonstrate the drawback here, because if I ask you, for example, this is also in audio data, you will have the same drawback. So this is because there is no magic. There is only a different way to see matching the application. Okay. Let's see if I can see. So if I ask you now, what is the T-shirt color of this guy? You can put all the AI want in the cloud or whatever. You cannot have this information. So the benefit that you get on the less data, you pay it somewhere. This is no magic. Here, you lose the information of the color, for sure. Impossible to reconstruct. So I know people are doing reconstruct, yeah, okay. But they guess. The AI is guessing. If pass a black person, a white person, and was trained in a white and black, is doing the opposite for sure. And you can see here. But why we need to put application? Because do you need here to tell me, I'm asking this because AI in physical need to be application specific. Do I ask, if I ask to the drone, see the hand and go away, I don't care which color is my hand. I need to see that it is going away. So this is because it's important efficiency at the application level that now is missing. But at application level, and I'm the first to say, if you come to me and say, I don't want to sell an event-based camera in general. I'm saying, tell me your problem. I'm telling you what is the sensor system that maximize the accuracy versus the latency. And I'm not religious. So even processor, I'm changing. If processor for Professor Benini, if it's bad, it's bad. I say, look, I'm taking another, but for this application, it's better. If you tell me you are a camera person, and you tell me I want to do with camera, you can do with camera. Maybe yes, but maybe it's different. And if you say for another application there is a better sensor, I trash it, I take another. This is also with a company I work like this. Infineon camera with radars, there is no Infineon around. I say what is good, and if you say no, but why you don't use instead of time of flight the Infineon radar? Because it's crap for this application. It's much better for vital sign monitor, it's much better for other things. I'm not a company guy. We need to maximize what you can do.
More questions? Everyone still amazed?
Okay.
And Stephanie?
What kind of programming environments do you use in order to work with these controllers?
In general, we try to go very low level. So it means, for example, to all the sensing programming, C language. So C. For all the AI, Python is today the best for PyTorch with all the environment. So I think this is the standard. For example, in this case, you can see we are using 3 different. So for all the camera sensor, there is Linux driver. For the robot, the ROS, the operative system for robotics. For, I think actually here is missing, but there is another part that we are using with the time of flight and In the radar sensor, C programming, because you need to stream the information before to a microcontroller, then going down. And for Jetson, it's more or less like Linux, C, between C and Python and CUDA, but more or less are, we try to go really to open all these boxes, because I feel this is the only way to give tools to the student to do different. Because again, if you can buy, this is what I say also to comment, if you can buy, don't come to me. Because it means that it will be more solid. You can see there is wired. So, but I think the student that are learning how to do it, they can go in company, be very innovative, and be, show that actually what they learn is useful. So actually, embedded system course that I moved to PBL, it's a 400 student course. I trashed all the board they were using to give STM32 microcontroller. So this is a board we did for them with C programming. Because I'm pretty sure in 2-3 years they will be back because they're using it in industry project, and this also because it's long term, and they are now start to bring back project to us, because in the meantime they grow in a company. So this also is, in my opinion, is good to teach, because if you teach, they will be back. I need to wait 10 years, but they will be back thanks you, because you teach them some things useful for what they are doing, and deep inside to be different, because they need to be a bit different. I hope so. I still didn't nobody come with a lot of money, but some are coming back. I hope one is coming with, become billionaire, and I will tell you in 10 years.
Last ask for a question. I don't see any, so I would like to prepare the closing with another warm applause for the fantastic Tom and the questions from the beginning. And so we will be able to continue here the conversation with Michele directly, also with Luigi, who is present with us, who is leading the research group here on the ITU campus. And for those participating online, I invite you to join next time in person, so we can also hear your questions. And with that, I'd like to close this network spotlight and make sure that also for the next 2 weeks, so 27th and 28th, there will be a double edition of the network spotlights. So we would be happy to see you and then engage in more scientific and also collaborative learning talks. Thanks a lot. See you next time.